Welcome back everyone to Approximation and Stability. Believe it or not, we made it through chapter 2, the crash course into functional analysis. Congratulations for getting this far. The fact that you made it means that you probably like mathematics, or you've got incredible ability to tolerate pain, frustration, whatever. In either case, you may now call yourself a mathematician, no matter what subject you study. Okay, now chapter 3, approximation methods. This is where this course really starts. And yeah, let's get started with this. So recall that in this course we are studying 3 classical problems of linear algebra. The first one of them is solving linear equations ax equals b. The second one was so-called least squares problems when equality cannot be achieved here. And the third one was eigenvalue problems. So this problem, this section 3, chapter 3, is about the first with equality here. But in chapter 3, we will learn methods that will turn out useful for also the other problems that I just mentioned. Okay, so let's recall our settings. So when we write ax equals b, then we are given an operator a, which is a linear operator from, well, let's say a vector space x into a vector space y, and we will assume this to be invertible. The other thing that is given is the right-hand side b here, and that is just an arbitrary element of y. Could be anything from y. And of course, the aim is to find this solution x here, and this is clearly an x, and well, of course, such that the equation holds. The fact that our operator is invertible implies that such a solution x exists and is unique. So it's all about finding this particular element x of capital X. And the trouble is that, well, typically in functional analysis, both of your spaces, or at least one of your spaces, x and y, have infinite dimension, which makes the representation of your operator A an infinite matrix. And of course, that exceeds the capacity of your computer and you need to do something else. So typically you come up with the following strategy. Instead of your operator A behind the infinite matrix A, you're using somewhat simpler operators A1, A2, and so on, and you're using a whole sequence that somehow approximates your operator A. And the word simpler here means that usually we take these operators from fxy, which denotes our set of operators of finite rank, and that is of course because we have finite storage. Okay, and then corresponding to the way how you simplify the operator from a to an, you will also want to simplify your right-hand side b into something that you call bn. So this also gives you a sequence b1, b2, and so on in your space y, where the operators an approximate your operator a, and the right-hand sides bn approximate your right-hand side b. Now with these simplified objects, operators, and right-hand sides, you can form simpler equations, and of course you're trying to solve these instead. Okay, so you're replacing your complicated, because infinite system, by a whole sequence of simpler, because somehow finite systems. But now of course you've got many of them. Okay, and when we say try, then this always says that we might fail. So in particular, we are hoping, but cannot guarantee yet, that these simpler equations will have solutions. And like in the case of our original equation, we are hoping for unique solutions. Okay, and the other point is, of course, that these unique solutions will converge to the unique solution of our original equation that we are actually looking for. Okay, well, maybe we can relax our goal a little bit, because when you're talking about convergence, then you know that in a convergence sequence, the first finitely many entries of that sequence just have no influence whatsoever. So it should clearly be enough if these unique solutions exist for sufficiently large n only. Let's not worry about the first 100 n. Okay, and this brings us to our first definition in this new chapter. We say that the operator sequence an is applicable. You could also say applicable. Both are fine. To our operator A, if the strategy that we wrote down above is working out, which means our two hopes 1 and 2 are coming true, for every right-hand side B, and all sequences of right-hand sides approximating B that are used here. Okay, when we write Bn converges to B, then what we mean is convergence in the space Y that is equipped with a norm, let's say the norm of Y. And it remains to discuss what kind of convergence we are expecting on the operator side. But at first glance, this seems pretty obvious, because of course we can do just the same like we are doing here. So let's write this down in a definition. For an operator A and the sequence A1, A2, and so on, let us write An converges to A, and let's put a double arrow here and speak of uniform operator convergence. If our sequence An converges to the limit A in the norm of the space Lxy, that is just the operator norm. Okay, and the fact that we are giving this particular kind of convergence 2 arrows shows that this might not be the last word in this regard. For completeness, we should of course also explain that this convergence here is meant in the sense of convergence in the norm of your space capital X. Okay. Now in our section on compact operators, we identified a problem with this approach. If this depicts the set of all bounded linear operators from x to y, then the set k of x and y of all compact operators from x to y is a proper subset, unless we are talking about finite dimensional spaces x and y here, which we don't. Okay, and then another subset of k of x and y is the set of all finite rank operators f of x and y from x to y. And we learned that compact operators cannot be invertible, so the set of all invertible operators must be somewhere outside the compact ones, so that the operator A we are trying to approximate is somewhere here. But like we said before, the simpler operators that we are using for approximation, A1, A2, and so on, are finite rank usually. So that our goal is to approximate this invotable operator here by a sequence of finite rank operators. But the trouble is that the set of all compact operators is closed with respect to that kind of convergence here. So if you have a sequence inside the compact operators and it converges uniformly, then also the limit will be compact. So you can't get through that boundary. Or to phrase it differently, the binding between that sequence AN and that operator A by uniform convergence is so strong that you cannot seriously expect to replace your complicated equation AX equals B with an invotable operator A by a sequence of equations with finite rank operators AN. So we will soon learn how to make that binding between the sequence AN and the limit A, meaning the convergence, weaker, so that it's indeed possible to approximate our invotable operator A by a sequence of finite dimensional or finite rank operators. But as I said, that needs another weaker kind of convergence. But before we will introduce that weaker kind of convergence, let's say that, well, at least in some rare cases, it's possible, also numerically, to deal with replacement operators AN that are not of finite rank. And in fact, not even compact, because then you would still have the same problem as before. And one prominent example of such a case that you fairly often see in applications, we will also discuss one of these applications in, I guess, week 8 or 9, is when your operator A is of the form identity operator plus a compact operator. So because your identity operator is invotable, and of course you can only discuss it when x equals y, then a compact perturbation of the identity might or might not still be invotable. So there's a good chance for this A to be an invotable operator. And then people from numerics will say, okay, we can deal with that identity part here. I mean, we don't need to approximate or to somehow store the identity operator. We know what it does, even though it's infinite dimensional. So we only have to approximate that compact operator down here. So you may choose your approximating sequence AN as identity plus KN, where these KNs will be again compact operators, possibly finite dimensional. Okay, and then there is nothing wrong with approximating a compact operator K in here by a sequence of, well, maybe finite dimensional operators K1, K2, and so on in here, even by uniform convergence, because F is not closed under that convergence. Okay, but if you have uniform convergence here, then you will have uniform convergence here. Okay, so in some examples, and some even important examples, it's possible to have uniform convergence of your sequence AN to your operator A, but it's just not great as a general concept. So let's for the moment stick to the situation where we have uniform convergence, and let us then study how chances are that this strategy will work out, or in other words, that our operator sequence will be applicable to the operator A.